Section. Introduction. We're going to delve into the world of global optimizers, which are designed to solve problems that involve an objective function, inequality constraints, and equality constraints. These elements may not always have desirable mathematical properties like linearity or convexity, and the decision variables could be either continuous or integer. In the literature on global optimization, most strategies try to solve the problem by approximating it with more manageable optimization forms. They often use a mix of gradient-based methods, outer approximations, relaxations, and mixed integer optimization, (MEO). For example, the well-known nonlinear optimizer CONOPT uses a gradient-based approach. It first finds an initial feasible solution using heuristics, then performs a series of gradient descent iterations, and finally confirms optimality via bound projections. During the gradient-based part of the algorithm, CONOPT linearizes the constraints and performs a series of linear search gradient-based iterations, while maintaining feasibility at each step. Another approach uses outer approximations, which simplify the problem by approximating the constraints with linear and nonlinear cuts, while preserving the initial feasible set of the problem. However, this approach can only be used with constraints that follow a specific mathematical structure, such as linearity of integer variables and convexity of the nonlinear functions, or concavity and bilinearity. Despite their effectiveness in some scenarios, these approaches have not found widespread use as they are limited to certain types of problems. The commercial optimizer Baron uses a different approach, combining MEO with convex relaxations and outer approximations. It uses a branch and reduce method, which divides the domain of the constraints and objective into subdomains, and tries to bound the decision variables in each subdomain based on the mathematical form of the constraints. This approach creates a branch and bound tree that guarantees global optimality, similar to the process used for solving MEO problems. The popular solver Antigone uses a similar approach. It first reformulates the problem, detects specific mathematical structure in the constraints, and then uses convex underestimators in conjunction with a branch and cut method to recursively find the optimal solution. While these approaches are effective for certain types of global optimization problems, they each have their own limitations. For example, gradient-based approaches rely on good initial feasible solutions and struggle with integer variables. Approaches that use relaxations and outer approximations are limited to specific types of nonlinearities, making them ineffective against more general problems. Finally, approaches that use branching or MEO-based methods are hampered by the curse of dimensionality due to their combinatorial nature. Moreover, for efficiency reasons, many global optimizers only allow constraints that use a subset of all the mathematical primitives. For example, the optimizer Baron can only handle functions that involve exponential, logarithmic, and certain other operations. However, real-world problems may contain constraints with a much richer set of primitives, such as trigonometric and piecewise discontinuous functions, where it is not always possible to reduce the problem to a form compatible with the global optimizer. Such optimizers are generally ineffective in cases where the constraints are black box and lack an analytical representation. These cases may arise in simulation-based constraints. To address these scenarios, a global optimization framework called OCTHaGOn was proposed. It attempts to solve general and black box global optimization problems by combining machine learning with mixed integer optimization, MEO. The framework can theoretically be used in problems that involve any type of constraints, such as convex, non-convex, implicit, and constraints that involve very general primitives. The only requirement is that the decision variables involved in nonlinear inequalities are bounded. Under this assumption, OCTHaGOn first samples the nonlinear constraints for feasibility and trains a hyperplane-based decision tree on those samples. It does this for every nonlinear constraint and then uses the MEO representation of the resulting decision trees to construct an MIO approximation of the original problem. It then solves the approximating MEO and uses a local search projected gradient descent method to improve the solution in terms of both feasibility and optimality. Despite the generality of this approach, the framework sometimes yields infeasible or suboptimal solutions due to its approximate nature. Therefore, in this paper, we provide extensions to OCTHaGOn to improve both the feasibility and optimality of the generated solutions. We enhance the framework by using adaptive sampling, robust optimization, constraint relaxations, and a variety of MI-representable ML models to create better approximations of the original problem. We test the enhanced framework in a number of global optimization benchmarks, and we show improved optimality gaps and solution times in the majority of test instances. We also compare against the commercial optimizer Baron, showing improvements in a number of instances. Section Summary. Global optimization problems often involve objective functions and constraints that lack desirable mathematical properties, such as linearity or convexity, and may have continuous or integer decision variables. Existing approaches, such as gradient-based methods, outer approximations, and mixed integer optimization, have limitations in terms of handling different types of problems. To address this, the OCTHaGOn framework combines machine learning with mixed integer optimization to solve general and black box global optimization problems, allowing for constraints with various mathematical primitives. The framework samples and trains decision trees on the nonlinear constraints, constructs an MIO approximation of the problem, and uses a local search method to improve feasibility and optimality. Extensions to OCTHaGOn, including adaptive sampling, robust optimization, constraint relaxations, and different ML models, further enhance the framework's performance in terms of solution quality and computation time. Section: Machine Learning and Optimization. We've been exploring the relationship between machine learning and optimization, a field that's been gaining a lot of attention lately. We've looked at various optimization methods from a machine learning perspective and seen how core machine learning tasks like classification, regression, and clustering can be framed as optimization problems. Machine learning has been instrumental in helping us tackle complex, large-scale optimization problems and has also been used to speed up tree search and guide branching in mixed integer optimization (MIO) problems. One of the most relevant studies to our work is the framework of constraint learning. This approach involves learning functions from data using MIO models, incorporating these learned functions as constraints in an MIO problem, and then solving the MIO in a way that satisfies these data-driven constraints. This method has been used to create food baskets for the World Food Program that meet data-driven taste preferences. We've adapted this constraint learning approach to solve global optimization problems in a framework we call OCTHaGOn. This involves sampling the nonlinear constraints and learning the nonlinearities using MIO decision trees. These decision trees are then embedded as constraints into an MIO problem that approximates the original problem. Once a solution to the MIO is found, we make local improvements to account for any infeasibility and suboptimality that arise from approximation errors. Our approach to solving global optimization problems improves upon OCTHaGOn in several key ways. We've expanded the types of machine learning models used as constraint approximators to include support vector machines, gradient-boosted trees, and multi-layer perceptrons. We've also developed a method for choosing which model to use for each constraint. We've introduced an adaptive sampling procedure that generates high-quality samples of the nonlinear constraints for more accurate constraint approximations. This procedure uses decision trees to oversample areas of the nonlinear constraints that are difficult to approximate. Sometimes, the machine learning-based MIO approximation of the original problem can be infeasible. To address this, we relax the constraints of the resulting MIO in a way that makes the MIO approximation feasible if the original problem is also feasible. We also use robust optimization to account for the uncertainty of the sample-dependent training of the machine learning models. We try to model the uncertainty in the trained parameters of the machine learning approximators and then use robust optimization to correct for this uncertainty. We've tested our framework on a variety of global optimization instances, and our results show that our enhancements improve the optimality gaps or solution times of OCTHaGOn in most cases. We've also found that our enhanced framework provides better or faster solutions than Baron in many instances. Despite its approximate nature, our enhanced framework is a promising method for finding globally optimal solutions. It can be applied to problems with convex, non-convex, and even implicit and black box constraints, with the only requirement being that the user needs to specify bounds for the decision variables. This makes our method suitable for problems that are incompatible with traditional global optimizers like Baron and Antigone. Our method is an extension of OCTHaGOn, which attempts to solve global optimization problems using a combination of machine learning and MIO. It creates decision tree-based approximations of the nonlinear constraints, embeds these approximations in an approximating MIO, and then solves and improves the solution resulting from that MIO to obtain a high-quality solution of the original problem. OCTHaGOn can also be used to solve problems with very general black box, implicit or even data-driven constraints. The only requirement is that the user of the framework supplies bounds for the variables involved in the nonlinear constraints. If such bounds are not provided, the quality of the solution returned by the framework can be adversely affected. Section Summary. The interplay between machine learning, ML, and optimization has been an active area of research. ML has been used to aid in the formulation and solution of optimization problems, such as assisting with difficult and large-scale formulations and speeding up tree search. A relevant framework called constraint learning proposes a systematic way of learning functions from data, embedding them as constraints in an optimization formulation, and solving the resulting problem. Our approach extends this framework by using different ML models, employing adaptive sampling for more accurate constraint approximations, relaxing constraints to address infeasibilities, and utilizing robust optimization to account for uncertainty in the ML models. Our results show that our enhanced framework improves optimality gaps and solution times compared to the original framework, and it can be applied to a wide range of problems with different types of constraints. Section: Algorithmic process. Our OCTHaGon method is designed to tackle problems where the functions can be non-convex. We aim to create and solve a mixed integer optimization (MIO) approximation of the problem through several steps. 1. Creating a standard form problem. We first separate the linear and nonlinear constraints. We also identify the constraints that set clear limits for every variable involved in a nonlinear constraint. If a variable doesn't have a clear limit, we try to calculate it by minimizing or maximizing that variable, subject to the linear constraints. Having clear variable limits is crucial for the next step. After determining the variable limits, we rewrite our original problem into a new form. The linear constraints of this new formulation are directly passed to the MIO approximation, while the nonlinear ones are approximated using the following steps. 2. Sampling and evaluating nonlinear constraints. For each nonlinear constraint, we generate samples. To choose the points where the samples are evaluated, we use three sampling methods: boundary sampling, Latin hypercube sampling, and KNN quasi-Newton sampling. Boundary sampling samples the corners of the hyperrectangle formed by the bounds of the decision variables. Latin hypercube sampling is used to obtain constraint samples from the interior of the decision variable hyperrectangle. Finally, KNN quasi-Newton sampling is used to sample the boundaries of the constraints, given the already generated samples from the previous steps. 3. Training decision trees. We train hyperplane-based decision trees on the datasets to approximate the feasibility space of the nonlinear constraint. If we have a nonlinear objective, then this objective is approximated with regression trees instead of classification trees. 4. Generating MIO approximation. The trained decision trees are transformed into an efficient MIO representation by extracting the corresponding hyperplane splits and then using disjunction formulations. The resulting representations are then embedded as constraints into the approximation MIO of the problem. 5. Solving MIO approximation. The MIO approximation of the problem is solved using commercial solvers, such as IBM CPLEX and Gurobi. 6. Checking and improving solution. The MIO is just an approximation of the original global optimization problem, so the solution can be near optimal and near feasible. To account for this, we first measure the feasibility of the solution with respect to the nonlinear constraints, then compute the gradient of the nonlinear objective and constraints, and finally perform a sequence of projected gradient descent steps to improve feasibility and optimality of the solution. We tested OCTHaGon against various benchmarks of the MINLP library, and found that in many cases, it performs well compared to traditional global optimizers such as CONOPT, IPOPT, and Baron. We also propose several improvements to OCTHaGon to enhance the quality of the solutions generated by the framework. These enhancements include enhanced sampling and evaluation of nonlinear constraints. We use boundary sampling, Latin hypercube sampling, KNN quasi-Newton sampling, and October-based adaptive sampling to sample the nonlinear constraints. Enhanced ML model training. For each nonlinear constraint, we train a series of MIO-representable ML models on the samples generated. We measure the accuracy of those models on a test set, and for each nonlinear constraint, we pick the model that demonstrates the best predictive performance. Enhanced generation of MIO approximation. For each nonlinear constraint, we take the corresponding ML approximator from the last step and represent it using an MIO formulation. Then, we embed all the MIO approximations into a unified MIO formulation. Introduction of robustness. To account for the uncertainty in the trained parameters of the ML constraint approximators, we utilize robust optimization. Constraint relaxation. In certain cases, the MIO approximation of the original problem is infeasible, due to the inexact nature of the constraint approximators. To account for this issue, we relax the MI constraints, while introducing a relaxation penalty into the objective. Enhanced solution improvement. Since the MIO solution can be near optimal and near feasible, we perform a series of projected gradient descent iterations to improve feasibility and optimality of the solution. In this step, we also conditionally use momentum to reduce the chances of landing in local optima. Section summary. The OCTHAGON algorithm addresses optimization problems with non-convex functions by creating and solving an MIO approximation in several steps. These steps include generating a standard form problem, sampling and evaluating nonlinear constraints using various methods, training decision trees to approximate feasibility, generating the MIO approximation, solving the MIO approximation using commercial solvers, and checking and improving the solution. The authors propose enhancements to OCTHAGON, including adaptive sampling, training multiple ML models, introducing robustness through robust optimization, and constraint relaxation. Section. Enhancement 1. ML Model Training. Let's delve into the first enhancement of the OCTHAGON framework, which is the training of machine learning models. The framework uses these models to approximate constraints and integrate them into a common mixed integer optimization (MIO) model. The OCTHAGON framework primarily uses decision trees based on hyperplanes, which are an advanced version of classification and regression trees, CART. However, these aren't the only models that can be used for constraint approximations. There are several other types of MIO representable machine learning models, such as linear regression models, support vector machines, SVMs, random forests, gradient boosting machines, GBMs, and multi-layer perceptrons with ReLU activations, MLPs. Given that different models have their own strengths and weaknesses, we decided to include a broader range of models, such as SVMs, GBMs, and MLPs. We also use a cross-validation procedure to decide which model type to use for each constraint. All the machine learning models we use support both classification and regression. For nonlinear objectives, we create samples and train a regressor on these samples. For nonlinear constraints, we create samples and train a classifier on these samples. Let's look at some of these models in more detail. 1. Support vector machines, SVMs. These models use a suitable hyperplane to make predictions for either classification or regression. For this work, we're only considering linear SVMs without any type of kernel, as our goal is to generate linear and tractable MIO approximations of the constraints. 2. Decision trees. These models partition the observation space into disjoint leaves after a sequence of splits. They are known for their interpretability and their ability to model nonlinear relationships in data. We use a generalized version of decision trees which includes hyperplane splits. 3. Gradient boosting machines, GBMs. These models can be represented as ensembles of base learners, where each learner is trained sequentially to correct the mistakes of the previous learner. We focus on decision trees as base learners, which are used most often in practice. 4. Neural networks. Specifically, we consider multi-layer perceptrons, MLPs, with rectified linear unit activations, ReLU. These networks consist of an input layer, several hidden layers with ReLU activations, and an output layer. They are known for their high representational power and ability to model very complex nonlinear constraints and objectives. Choosing the right model type for each nonlinear function is crucial, as this choice heavily determines the quality of the resulting MIO approximation. To make this decision, we use a cross-validation procedure. We train all model types on samples of the nonlinear function, measure their performance on a test set of unseen function samples, and choose the model that performs the best. Finally, we approximate every nonlinear constraint and objective using the MIO representation of the best performing model. This results in an MIO approximation of the original optimization problem, where the nonlinear functions are replaced by MIO representable functions. Section summary. The OCTHAGON framework incorporates ML models into a common MIO by approximating constraints using hyperplane-based decision trees. Different types of ML models, such as SVMs, GBMs, and MLPs, are incorporated, and a cross-validation procedure is used to select the best model type for each constraint. Linear SVMs, decision trees with hyperplane splits, GBMs with decision trees as base learners, and MLPs with ReLU activations are described as MIO-representable models for constraint approximation. Section. Enhancement 2. Sampling. We're introducing an enhancement to our method, which we call sampling. The goal here is to improve the approximations of the nonlinear constraints by generating high-quality samples. These samples need to capture the nonlinear and non-convex feasible regions of the constraints, which means we can't just use a static sampling procedure. Instead, we need a sample generation process that adapts to the landscape of the function we're trying to sample. In our previous work, we used a three-step sampling procedure: boundary sampling, LH sampling, and KNN quasi-Newton sampling. The first two are static procedures, meaning they sample all functions in the same way, without considering the characteristics of those functions. The third, KNN quasi-Newton sampling, is more adaptive, as it uses the function output to sample the constraints on the boundaries of the feasibility region. For this enhancement, we start with the same three steps to generate an initial set of samples. Then, we propose an adaptive sampling method to generate even more detailed samples for the constraints. We call this method October sampling, and it works by iteratively resampling the constraint in areas where the learners can't approximate well. Here's how October sampling works. First, let's say we're trying to approximate a certain constraint, and we already have some samples for the feasibility of that constraint. The goal of October sampling is to resample parts of the constraint that are hard to approximate. To do this, we use hyperplane-based decision trees, which are one type of learner we use for constraint approximations. We start by training a learner on random subsets of the dataset. Then, we identify samples where there's a high level of disagreement between the predictions of the learners. These samples indicate areas where our learners aren't generalizing well, and are therefore worth resampling. Next, we identify polyhedral regions where these ambiguous samples reside. In a hyperplane-based decision tree, each leaf is represented by a polyhedron, and the polyhedra of different leaves don't overlap. So, the decision tree assigns each point to exactly one leaf polyhedron. For each ambiguous sample, we find the intersection of the leaf polyhedra of the different trees. This gives us a set of polyhedra, each of which has the property that any point within it will have a certain level of disagreement in the predictions of the trees. The next step is to generate samples from the interior of these polyhedra, which represent areas where there's a high level of disagreement between the predictors. To do this, we use the hit-and-run algorithm, a Markov chain Monte Carlo method for generating samples within a convex body. This involves picking a starting point within the polyhedron, generating a random direction, calculating the minimum and maximum values for a certain parameter, and then picking a value for that parameter at random to generate a sample. We repeat this process until we have the required number of samples. Finally, we generate samples for all the polyhedra. If the same polyhedron appears more than once, we only sample it once. The goal of this procedure is to generate samples in areas where the tree learners are uncertain. By doing this, we hope to improve the generalization of machine learning models and create better constraint approximators. This sampling procedure is adaptive and can be repeated to iteratively generate more refined samples and more accurate approximations. Section Summary. In order to accurately approximate nonlinear constraints, we propose an adaptive sampling method called October sampling. This method involves training hyperplane-based decision trees on random subsets of the dataset and identifying ambiguous samples where there is a high prediction discordance between the learners. We then generate samples from the interior of the polyhedra representing areas of disagreement, using the hit-and-run algorithm. This iterative sampling procedure aims to improve the generalization of machine learning models and create better constraint approximators. Section. Enhancement 3. Relaxations. We've made a few enhancements to our approach to global optimization problems. The third enhancement is about relaxations. As we've discussed before, we start by creating a mixed integer optimization, MIO, approximation of the original problem. We then optimize this MIO to get an approximate solution. To improve this solution, we perform a local search projected gradient descent, PGD, step. However, there can be instances where the MIO approximation is not feasible, even if the original problem is. This can happen if a constraint is very hard to satisfy, leading to very few feasible samples. In such cases, the learner might approximate the constraint as infeasible almost everywhere, resulting in an infeasible MIO. To address this, we relax the MIO approximation to ensure it always has a feasible solution, as long as the original problem is feasible. We introduce relaxation variables and a penalty parameter into the MIO. The penalty parameter determines how much to penalize relaxed constraints. The higher the penalty, the more the MIO solver will prioritize solutions with smaller relaxation variables, resulting in fewer relaxed constraints. However, it's important to note that we first try to solve the problem without relaxations. If the MIO approximation is infeasible, we then use the relaxation technique. The fourth enhancement is about robustness. When using machine learning (ML) models to approximate nonlinear functions, there can be a lot of uncertainty in the learned model parameters. Training on different sample sets can lead to different model parameters and thus different approximations. To account for this, we use robust optimization (RO) when incorporating the ML learners into the final MIO. RO is a method used to handle uncertainty in the data of an optimization problem. In our case, we use RO to handle uncertainty in the trained model parameters. We model this uncertainty using a specific uncertainty set. The way we define the uncertainty varies across different models. For support vector machines, SVMs, we model the uncertainty in the coefficient vector values after training. We use multiplicative uncertainty to scale the coefficients proportionally to their nominal values. If an SVM is used to approximate a constraint, we approximate it with an uncertain constraint. This constraint can be equivalently written using certain mathematical tools. For decision trees and gradient-boosted machines, we model the uncertainty in the coefficient vectors of the hyperplane splits. We again use multiplicative uncertainty to scale the coefficients proportionally to their nominal values. This is crucial as it allows us to keep the zero elements of the coefficient vectors constant. If we want to approximate a constraint with a decision tree, the splitting constraints take a certain form after accounting for uncertainty. These constraints can be equivalently written using certain mathematical tools. For gradient-boosted machines, we enforce the constraints to each individual tree learner of the ensemble. We ensure not to use too many learners in our ensemble to avoid infeasibilities that arise from enforcing robustness in all learners at the same time.